Hi everyone and welcome to my video on antidifferentiation of polynomial functions. Yes, it's a continuation of our differentiation and integration section of the Year 11 Mathematical Methods course here in Australia. Now, if you're not here in Australia, don't worry about it because differentiation and antidifferentiation, or integration, is universal, and so this lesson will probably be just as useful. My name's Darren from Maths Guru. Thank you very much for finding this video. Hopefully you're going to find it useful. Now, behind me we have the learning objections. Oh yes, we're going to know what it means to antidifferentiate, understand what the notation is for antidifferentiation, know what the rules are, and know how to use your CAS. Now, having done that, let's get moving on. Now, recap of past learning pretty much is all the stuff that has gone before. So we've looked at differentiation, which is really the process of finding the gradient of the tangent at a point on a graph. That is so critically important. It is nuts. Okay, now as the course progresses, we use it over and over again, and later on in this particular section we'll start applying it to real world problems. And of course, in an exam, that's what we're going to do to you with real world problems. Yes, but there's gradient functions and there's all sorts of stuff as well. But then we get to antidifferentiation, which is the opposite of differentiation, which is probably why it's called anti. Now, before I go any further, can you do me a massive favor? If you're already a long time watcher of this channel, you know I'm going to ask you to subscribe if you haven't already done so. Subscribing to my YouTube channel is actually massive because I sit here talking to myself. It's maths videos. No one watches maths videos except for you. And clicking that little button really does just say to me at the end of the day, hey, you've gained 3 extra subscribers. By the time I get to 10 extra subscribers, I fall over and have a lie down and the dog thinks I'm actually just dead. Whole new discussion. So if you can do that, that will be great. Okay, so now let's look at differentiating the constant. All right, so when we've been learning about differentiation, what do we have? Well, we got y is equal to x squared plus 2. So y dashed, which can also be written as dy by dx and any other variation that we've already been covered in the previous parts of the course, can be now what? Well, okay, what do? We multiply the power by the coefficient, and it's not a coefficient of 0. Don't get tricked. That's a coefficient of 1. So 2 times 1 gives me 2. Then we write the pronumeral and we take 1 off the coefficient. So 2 minus 1 is 1. Don't really need to write that, but that's okay. We can do that. And then people tend to get a bit tricked with this one here. If you remember, that is 2 times x to the power of 0. To be able to differentiate, you have to have a pronumeral. Okay, well, that's all right because x to the power of 0 is 1. So now we can do 0 times 2, which is 0, times x, and then take 1 for the pronumeral, from the power, gives me 0 times x to the power of minus 1. Okie dokie, well, that's going to be 0. And we already knew that, didn't we? Because we know that where there is a constant, it differentiates to 0. And this is just really why it differentiates to 0. Now let's look at y is equal to x squared minus 6. And if your brain is already working the right way, you're going to be saying, hold on a moment, there's some sort of translation going on there. Yeah, let's go there in a minute. So we've got y dashed is equal to 2x to the power of 1. And again, that would, hold on a moment, do you notice something? Well, I've got y dashed there was 2x to the power of 1, and I've got a y dashed there. But they were different functions, weren't they? Well, yes, they were. And if we were to draw them on the same set of axes, this is what we'd actually see. Here's my graph of x squared plus 2. Here is my graph of x squared minus 6. But the point of it is that plus 2 and minus 6, all it did was vertically translate my graph. It didn't actually change the shape of the graph in any way, shape or form. So if I was to now choose an x value of, what is that, 3, and look at that point there, and the same point above it, and took the gradient of the tangent at the line, it would be exactly the same. And that's why we have for this graph here that y dash is equal to 2x, and here that y dash is equal to 2x. It's the same function. We've just translated it. Now, obviously, by the time we start to dilate it, then we will end up with different gradients at the same points, but that's probably a little bit outside of what we're going to do here. So what we notice is for any of these family of graphs that had y equals x squared plus or minus some sort of a constant, it will always have a gradient function of 2x. And hopefully now I've explained why, because that vertical translation is going to mean nothing. It's not going to change the actual shape of the graph. And so the gradient at every point will be the same. Now, obviously, in this situation, when we differentiate a constant, it becomes to 0. But what if we had to reverse it?